How are we doing, everybody? I was just sitting here jamming to some Ed Sheeran, and I thought, hey, you know what would go great with this Ed Sheeran? Some math. So here we are. 5.3, solving trigonometric equations. So we looked at actually manipulating trig expressions to verifying trig identities, to now we're actually going to take that skill and move it into solving trig equations. So blending together kind of the end of chapter 4 with the beginning of chapter 5. So this is a lot of algebra. It's a lot of manipulation. All the rules are all the same, but you know, the thing that trips people up is just the fact that, again, it says sine, cosine, or tangent instead of an x. All right. So if I look at something like this, 2 sine of x minus 1, essentially it's like 2x minus 1 equals 0. And what would I do? I would try to get x by itself. I would add 1 to both sides, and then I would divide by 2 on both sides. That would give me x equals 1/2. So I'm going to do the exact same thing with this function. I'm going to add 1 to both sides and divide by 2, but what that leaves me here is sine of x equals 1/2. Right? So now I'm at this place where I don't know what to do, because you know, if this was multiplication, I would know to divide. If it was addition, I would know to subtract. If it was division, I would know to multiply. But I have something different going on here. I have the sine of x, when in reality I just wanted to say x. So in order to take care of this, just like with multiplication comes division, just like with subtraction comes addition, the opposite operation to the sine is the inverse sine. Inverse sine on this side as well. So I take the inverse sine of both sides, and what do I have here? I have the composition of functions. One is the inverse of the other, so what's left here is just the variable. And what's left over here is the inverse sine of 1/2, which is the question, what angle gives a sine value of 1/2? And if we return to our trusty unit circle, or hopefully at this point, you know, we're getting good at this, and we can figure out exactly where that is, and we know it in our mind. That's at pi over 6. And then the question is, does the sine have 1/2 at any other places? And the other places that happens are at 5 pi over 6 as well. Okay, so our solutions here are x equals pi over 6 or x equals 5 pi over 6. Let's go ahead and try it out up here. If I were to do x is pi over 6, that would be 2 sine of pi over 6, which is 1/2, minus 1. That's 1 minus 1 equals 0. Perfect. And what if I did 5 pi over 6? 2 times sine of 5 pi over 6 is 1/2, minus 1 equals 0. Good. So these two solutions work. Now there's also something else that we have to add to these solutions, because these aren't the only two places that happens. If I take an image of a unit circle here, we're looking at about here and about here, these two spots. Now that's a rotation of pi over 6, this is a rotation of 5 pi over 6, but what about if I were to rotate all the way around and then pi over 6? Or all the way around and then 5 pi over 6? Or for that matter, what if I rotated twice and then pi over 6? Or 3 times and then pi over 6? So with that in mind, I can't just say that these are the only two places that would work. There are other angular values like pi over 6 plus 2 pi that would work, or 5 pi over 6 plus 2 pi that would work. And in fact, plus 2 pi as many times as you want to. I could say 16 pi, because that would be 8 full rotations around. So I'm going to represent that by adding another variable onto the end of it, 2 pi n, which means as many rotations around the unit circle as you like to. As long as you add pi over 6 to it, it'll be a solution. Or however many rotations you like to around, as long as you add 5 pi over 6 to it, it'll be fine. Alrighty, so the algebraic parts of finding these solutions can be really easy. Sometimes they can be a little bit more difficult, as we'll see in the next example. But what's really, really important is that you understand this portion. You got your solutions, but you need to understand those aren't the only solutions, because these functions are periodic, because they're cyclic and they continue to go, they continue to rotate. There will be an infinite number of solutions. Okay, just as we can see on this this graph here, I had pi over 6 and 5 pi over 6 as my answers, but because these functions continue to move and continue to move, I also have this one, 5 over 6 plus 2 pi, and 5 over 6 plus 2 pi, or going in the negative direction would have worked as well. And there'll be another 2 over here, there'll be 2 more over here, forever and ever. Some of the algebra gets a little bit harder. We have equations in a quadratic type like we saw in the previous sections where you had to factor them. Now this is going to be happening in the context of solving. So for example, we have an equation that's 2 sine squared of x minus sine of x minus 1 equals 0. Right, so it's not a terribly difficult equation to simplify if we think of sine of x equaling some variable. So this will be 2u squared minus mu minus 1. So if I'm trying to just factor something like this, the factoring actually becomes a lot simpler because it's just going to end up being 2u plus 1 and u minus 1. Now it's very possible that some people might need refreshers in factoring. I probably should have said this in some of the earlier videos. I probably will have addressed it with most of you already. But if you need refreshers in factoring and factor by grouping, you need to let me know so that we can solve that and fix that. But most people should be able to factor these out pretty easily without issue. So when I replace the u again, I have 2 sine of x plus 1, and I have sine of x minus 1. So that's my factored form, and that still equals 0 this entire time. Now, what do I do from here? If you remember, there's something in Algebra 1 called the zero product property, which basically tells you that if I have two things multiplying and it equals 0, one of those two things has to be a 0. So I have to set up two possibilities. 2 sine of x plus 1 equals 0, that's this case, or this one, sine of x minus 1 is the one that equals 0. And now I have two much simpler equations. This one over here turns out to be sine of x equals negative 1/2, and this one over here turns out to be sine of x equals 1. And now it's a matter of solving and finding solutions. In this case, I'm looking for where, oops, I still have to take the inverse sine on both sides in order to undo the sine. Inverse sine. And on this one, an inverse sine. Inverse sine. So what are we looking for? On this one, cancel, I get the x by itself, and I'm looking for a place, an angle value, where the sine is negative 1/2. This is very much like the last one that we did, where if I look on a unit circle, ching, ching, I'm looking here and here. So it's pi over 6 down this way, or pi over 6 down from pi over here. My two possibilities end up being 7 pi over 6 or 11 pi over 6. And then, over here, I'm looking for where the sine value equals 1. So what angle gives me a sine value of 1? And that should be simple for most people. The x is pi over 2, because pi over 2 right up here at the top is the only place that sine equals 1. Now, the grand question. In the last one, I did this thing where I added 2 pi n to the ends of all of these. I'm not going to do that this time. The question being, why? Give you a second, maybe you can figure that out. That right there. I'm only looking for the solutions on the interval 0 to 2 pi. I'm not looking for all solutions ever to happen. I'm just looking for the ones between 0 and 2 pi. So I don't need to worry about the ones that happen after that, or before that even. Alright? So make sure that you read the entire set of directions and you understand that boom, boom, boom. 3 answers to this one. It's not infinite. Now let's look at ones with multiple angles. Now this happens when I have a simple equation and it says 2 cosine 3t minus 1 equals 0, and I add 1 and I divide by 2 and I get cosine 3t equals, let's say that's 1 1/2. And then I'm stumped. because I've never seen this before. At this point, it usually always says cosine of and then variable. So I'm not quite sure where I'm supposed to go with this idea, but let's just go with it and do exactly what I would have done last time. Let's do the inverse and see what we get. Okay, over here, these are going to cancel, and I'll get 3t. And over here, I'll get what angle gives me a cosine value of 1/2. So what we should get there is pi over 3, as well as 5 pi over 3. Okay, so hopefully we can get this far. Now, it's simply a matter that the equation isn't fully simplified. I still don't have t by itself. And I have two different solutions here, so I kind of have two different equations. And I don't think I'll write them out that way. 3t equals pi over 3, or 3t equals 5 pi, that's not 5, over 3. So how would you deal with this one? I have multiplication, so what would I do? I would divide. Dividing by 3 over here is a lot like multiplying by a third, which makes this pi over 9. And then over here, if I had dividing by 3, that would make that 5 pi over 9. So those are my two solutions here, pi over 9 and 5 pi over 9. Now the question is, do I need to add that 2 pi n portion onto it? And the answer here is yes, because I'm not looking at a specific interval. So plus 2 pi n for both of them. And oh geez, I'm going to throw a curveball in there again. Remember how we had to divide by 3 over here? We had to divide by 3 on this one? Well, we also have to divide the rotation, 2 pi, by 3. Because what we've essentially done by putting this value in here, if you remember graphing these trig functions, is that changed the period. So the period isn't actually 2 pi. The period is 2 pi over the b value, 2 pi over 3, 2 pi over 3. So I'm not adding a period of 2 pi anymore. I need to add the specific period to this equation, which is 2 pi over 3. So any rotation of 2 pi over 3 added onto this will be a solution. Any rotation of 2 pi over 3 added to this will be a solution. Alrighty, that's what happens with multiple angles. So as we can see here, in the 0 to 2 pi normal period that we see for the original function, this cosine function goes through 1, 2, 3 different periods. Alright, so the solutions that we would find are tripled. That is the last bit for 5.3. We went through a couple of different types of things. There are even more examples in your book that have different types of algebraic situations that you would see. I didn't really feel that it was necessary to go through all different types because it mainly is just algebra and rehashing algebraic technique. But if we have issues with the assigned problems, we will definitely go over it. We'll definitely work on it. And I will see you all in class next time. Bon voyage.
I think I need to go home.